Hello, everyone. Welcome to MACSMIN 2025. So, on the second day, Dr. Yury Elkin will talk about complete invariants of molecular graphs with continuous polynomial time metrics. Over to you, Yury, please.
Yes, so hello, I'm Yury Elkin, and today I'm going to talk about this project that I'm doing with the data science group of the University of Liverpool, and it's about distinguishing molecules geometrically, and we treat them as a graph. So let's go to the first slide. So we have molecular graphs in 3 dimensions that we model by simply 3D points in the Euclidean space, and then we also draw edges between the atoms when there is a covalent bond between them. And to classify them, we have this notion of equivalence relation. So when there's this relation between 2 objects that is reflexive, so it's always like it's always in the relation with itself, then it's symmetric. So if it's the relation with some other, then the other is relation with it, and transitive. So if there is this chain of relations like A, B, B, C, then A is in the same relation with C, then this type of equivalence relation partitions the sets of objects into disjoint classes. And particularly for our case, we need to find some kind of geometric separation or somehow classify them. And here are some examples. So there's like many ways of defining this equivalence relation. So we could simply look at the compositions, but then of course the problem will be that they're molecules with the same composition, but they're actually different molecules because of their geometry. So we need something like more strong than just the composition. And we will be actually looking at the equivalence by the rigid motion. So in 3-dimensional space, we will say that 2 objects are equivalent by rigid motion if we can translate and rotate one to another. And then, of course, there is this weaker equivalence relation that is called isometry, when we also allow reflections. But in this talk, we will be mostly focused on the rigid motions. So and to actually kind of go from the molecules to the classes, we have this notion of invariant that is simply a function from, in our case, from graphs to something more simple. And then, of course, we wish that if the 2 objects are the same, then we want them to be in the same class. And obviously, if the objects are not the same, or actually if the invariant is not the same, then the objects are not. So this is basically just an invariant. It's not a complete invariant yet, but this is just a general definition of it. And actually, we want something more stronger that is called complete invariant. So the complete invariance basically says that if if the invariant is the same, then the original graphs are the same. So it's a kind of injective function from the class of graphs to the partitions. And we can think, here's just example that we can think about it as DNA style code that uniquely identifies humans, although this is like not entirely true, because like there can be humans with the same DNA, but if we take like things out and so on, so this is like almost true. So then for the graphs, because this is how we model the molecules, our problem is to design this such complete invariant that we go from the graphs to something simple, some simple space. And then also we want this invariant to be Lipschitz continuous. So this basically means that if we go into the invariant space and then the two invariants are, or the image is very close to each other, then the original molecules are also close to each other. And here's like some more practical conditions. So there can be like completeness, so that the invariant of this G will actually contain all the symmetrical images of G. Then there's this invertibility, so that any graph G can actually be reconstructed. So if we have invariant, we can go back to the graph in some way. And obviously the computability is probably the most important, that actually we can compute this in a fast way. So there are many invariants that we can compute, but if it's like, if the time complexity is exponential, and so we wouldn't be able to use it on larger molecules at all. And the problem is also that usually we have a large number of molecules. We are not like looking at only one or two, we are looking at large sets. So obviously the issue of computability is like really important here. And
Yury, could you stop for a moment on the problem statement and check if there are any questions in the audience? Because there was an introduction with many abstract concepts, and now the problem is stated. So if you have any questions, it's convenient to ask, especially because Yury goes rather fast over the slides. Is the problem understandable? Yeah, we talked about isometries yesterday. Yeah,
sounds more like a metric than an equivalence class, because it says.
Yes, perfect.
Yeah, no, I'm just a little bit confused, because you said you want equivalence classes, but now you're talking about small changes, give small changes, so it's more like a metric space to me, just intuitively.
Yes, yeah, Yury, have you had the question?
Yeah, so
find only a metric, or do you look for something more than a distance metric between equivalence classes?
Well, so probably there's confusion, because like there's this Lipschitz continuity, which obviously like depends on the metric. So we have like invariant function which goes from the class of graphs to something, and obviously in the both ends, to have this Lipschitz continuity, you need to define some kind of metric. But here I haven't actually defined any metrics yet, I think.
Yury, maybe you could give a simple example of an invariant for a molecule, some integer valued invariant.
Well, for example, number of atoms in molecule.
Okay, so could you explain a bit more? So why it is invariant, whether it is complete, so why not it's not enough?
Well, yeah, so if we have if we have on one side we have basically molecules, then we take the invariant that simply counts the number of atoms. So it's not complete, because there is like many molecules that have, like, for example, 3 or 4 atoms, and there's like many of those. So actually we don't get that much from this invariant. And if it's continuous, then but it probably depends on the metric, so you probably can make it continuous.
Okay, so let me clarify. But the problem actually contains here two big parts. One part is an invariant. So Yury gave a simple example of an invariant. So when we say actually molecule in this talk, we mean molecular graph. So a graph embedded into a three-dimensional space. So invariant could be, for example, the number of vertices, the number of atoms in a given molecule, which is very simple. So constructing a strong invariant and eventually complete is already difficult. But we make the problem even more difficult by asking that this invariant changes continuously under perturbations of atoms in a suitable metric. So the metric has not been defined yet, but this is a second important part. Not only an invariant, but also a distance metric to measure the similarity or exactly a distance between two objects.
Yeah, I was confused because you compute invariant for the isometric class and not for an object. So.
Yes, for classes.
Mm.
Okay, so if there are no more questions, then Yury, feel free to continue, but not so fast.
Okay. Yes. Computability. Then we have this graphs against atomic clouds. So because we can treat the molecules just as atomic clouds, but obviously if we include the edge information or the information coming from covalent bond. So if there is a covalent bond between two atoms, then we draw an edge. And actually this kind of we get more information from this, but at the same time it's in some sense harder problem. Although I need to say that usually like the covalent bonds are, or sometimes they're not well defined, and they might actually depend on the distance. So I'm not sure how much more information we get, but this is something we can try and something we have done. Here is just introduction of this QM9 database on which we run the molecule. So there is this database of around 130,000 molecular graphs. There are, I think, molecules, but you can also get the covalent bonds from them. And they have up to 9 non-hydrogen atoms, and I think they can contain only like 5 atomic types. It was like hydrogen, then like C, N, oxygen, and F. And yeah. Then actually to understand this QM9 database and actually learn to separate the molecules or find some simple invariants or descriptors for those, we first introduced this simple sorted radial distances invariant. So basically what we do is that we have this, at this point we treat the molecule simply as the point cloud, and then we find the center of mass in it, and then we compute the distances from every atom to the center of the mass by the Euclidean distance. Then we get the distances, and we store the distances from the smallest to the largest one. And this way we get this simple invariant that is also very fast to compute, because we only need to make like one loop, or 2 loops basically. But so first to find the center of mass and then compute the distances. So it's very fast to compute and gives us a simple invariant. So here's some visualization for QM9 database. So here we have SRD1, which is like the I think distance from the closest atom to the center of mass, and here is like distance from the closest amine. Actually, Vitaly, do you remember that? Did we have actually from the largest one to smaller here? Because like here we have SRD1 minus SRD2, but the values are positive.
Yes, Yury. So it's convenient for global molecules to order with radial distances from the largest to the smallest. Well, simply because if an atom is accidentally at the center of mass, or more exactly, we compute the geometric center of all atoms, then we'll have value 0. Right? But we would prefer to capture the global shape of a molecule. That's why it's more convenient to start from the largest distances here. Yeah, could actually explain a bit more this very important transaction, because it's the simplest. And hopefully you could explain it in more details.
Okay, so here the SRDs are sorted from largest to smallest, and basically we have SRD1 value on the x-axis and y-axis. We have SRD1 minus SRD2. So SRD2 is the second longest distance from from the atom to center of mass, and then you simply put them in this map, and also we have this color bar here, which indicates that how many atoms this particular molecule have. So in some sense, we see that molecules that are smaller are usually have smaller SRD1 value, and the larger you have like bigger. But I think that this probably comes with no surprise, because the larger molecule we have, then actually more complicated gets, and then probably further away is the furthest point. So,
Yury, looking again at this plot, so you have some very simple molecules consisting of only 3 atoms, for example, in this plot. Can anyone guess where the water molecule is in this map? Our simplest and probably most valuable molecule in the universe, the water molecule.
Well, probably have 0, won't it, on the y-axis?
Yury, is it? Can we discuss the water molecule? I even have a model of that water molecule for you. Haven't seen it before. So only 3 atoms, 1 oxygen.
So the center of mass, do you consider the weight of the atom?
We can, but for our computations here, we take simply the geometric center for simplicity.
I think that makes a difference.
Actually, it makes very little difference. Yeah, of course, it will be slightly perturbed, but for, say, for comparisons, even for larger molecules, it's even for infinite crystals, when we take masses into account, it makes only little difference. So geometry in our studies turned out to be much more important. So looking again at this water molecule of only 3 atoms, so how many sorted radial distances do we have for this molecule of 3 atoms?
3.
Correct, Will. So we have 1 center of mass and then 3 distances from that center of mass somewhere inside with triangle to 3 atoms. So the first 2 will be, well, to what atoms here? Can you guess from that shape, which is, well, roughly correct, I guess. Like, does it look realistic? So about 105 degrees this angle, so a little bit obtuse. And yeah, since because of that isosceles shape, the first 2 sorted radial distances, the largest ones will be from the center of mass to 2 oxygens. Okay.
Hydrogens.
Oh, sorry, to 2 hydrogens, because oxygen is indeed in the middle. So our distance to oxygen will be smaller.
Yeah, but unless it's 8 times heavier, then I would say it's closer to the oxygen. No?
Right, but the conclusion will be the same. So the distance here to the oxygen will be very small. So it will be our SRD3, but the first 2 values will be equal also because of the symmetry for in this particular case. So that's why the water molecule will be on the horizontal axis in this plot. And can you guess where approximately, if you also explain, Yury, so what are the units? What are these numbers on the axis?
Well, they were angstroms, right? So,
and approximately 1 angstrom is the smallest interatomic distance between atoms, actually, not only in molecules, also in crystals. So that's why for a water molecule, which is rather small, it is projected simply to the leftmost point on that plot. So this is the first molecule in that waterfall image. So the red one also indicated, see here, by, it's a little bit small, but the color corresponds to 3 atoms.
You know what the other ones are that are like along?
We have identified a few of them. Actually, yes, it's a good idea maybe to include next time labels for some points, but we simply wanted to check the understanding what is going on.
If you had a triangle,
Second?
an equilateral triangle, where would you be on there?
Good question. Good question. So, Yury, what if our molecule ozone
O3.
O3? I think O3 is not in QM9. It's not in QM9, but a good question. What if you have an equilateral molecule of 3 atoms? Then what will be? Can you briefly describe the values SRD 1, 2, 3?
No, well, we'll simply have like 3 copies of the same value, probably.
Right, because it's an equilateral triangle, so the distance from the center of mass to 3 vertices will be equal. We could include more molecules by considering large databases. Any more questions on that particular plot? Okay, then Yury, feel free to continue.
Yeah, so so here is another plot. I think this is like SRD2 and SRD2 minus SRD3. Actually, this is a subset where SRD1 was the same as SRD2. So we actually zoom into that, and we have like similar case here that larger molecules tend to have like larger SRD2 value.
And here the water molecule will be in a different location, because indeed, as Yury mentioned, we take the subset which was on the horizontal axis in the previous plot, right? But now we consider sorted radial distances to the second and third atoms from the center of mass. So for the water molecule, that difference will be now positive. And the water molecule will be in a different location because it's a different projection into different coordinates. So any guess? Where is it in this plot? So as a hint, we have the color for the number of atoms. So it's again the dark red color for the water molecule. And to easily remember, it's again the...
It's going to be that one that's sort of at 0.4, is it? Or
yes,
something?
the leftmost point on that plot. So the most extreme molecule is again the water here. So these two plots demonstrates that we can project to different coordinates, but also we can zoom into any subset or hotspot and visualize this subset in different coordinates, so you could see more information for any molecular data set. Any questions so far? Okay, then Yury, feel free to continue to strong invariants.
Yeah. So we have the next. We have sorted pairwise distances. So before we had like a simple vector like from center of mass to everyone, but here this invariant is basically that we take all the pairwise distances and put them into a vector and sort them. I think again from this time from smallest to largest, I think. And and also like here in this variation, we don't yet take the edge information, but of course, it can be added by, for example, multiplying the ones with the edge by -1, but we will actually talk about this later, I think. But one important thing about this SPD is that it's complete when the points are in general position. So if the points are in such a way that there is no copies of distance, so if every distance is, I think, uniquely determined, then this is a complete invariant. But obviously, for molecules, there are a lot of symmetries, so it's rarely complete. So here we have just comparison between SRD and SPD. Yeah, so the SRD is obviously faster to compute. It's just linear complexity. So SPD has a quadratic complexity since we need all the pairwise distances. But since the molecules are small, I think it plays little role here because molecules are rarely like over 30. And then I think here we have some examples. So about when I think those points are not distinguishable by SRD, but are distinguishable by SPD. So do Vitaly remember this example?
Yes, so this example demonstrates, so from the previous slide, the same clouds of 4 points. So it's a very simple but single example when 6 pairwise distances are insufficient, but actually surprisingly, the simple invariant sorted radial distances easily distinguishes this particular case. So although SRD looks weaker, in that case, the numbers are different. So SPD doesn't distinguish them, but the simple sorted radial distances distinguish with clouds of 4 points.
Yeah.
Yeah.
So this is Harry invariant, and then so we can actually add the edge information by simply putting a minus sign when there is I think so plus is when there is an edge. When there is no edge, then we multiply it by -1, and this way we can actually encode the graph information, and it gives us more information about it. And the next one is I think a little bit harder. So again, we have a graph or a point cloud. It can be defined for both. Then we simply build a matrix based on we fix a point, and then we compute its distances to all the other points. And by doing so, we actually I think we put the matrix. I think we sort the points in every but we include all the points. And then we get this matrix, and then here we actually did this procedure of collapse, that if we have the same rows, then we have like larger coefficient. And I think that also those coefficients here have to sum to 1. And those objects, they're like fast to compute the invariance because basically we have a matrix, but then the metric between them is a bit more complicated. So we have this earth mover distance that can be computed for those. And obviously we can go with the assigned distances. So simply putting sign -1 when there is like, I think, yeah, when there is no h, then -1, there's +1. And also, when we have this metric, then luckily it's continuous in the sense that if the matrices are, or if the matrices are close to each other, then by perturbing them, then the original clouds are not that far away from each other. So and from the PDD, we move to a more stronger invariant. So here we fix a base P, and for every point we actually get we actually write this unordered pair of like distance from a point to center of mass of the point cloud, and also from this point to point P that we have fixed. And this way we actually have even stronger invariant by having those unordered set of those pairs that we can also treat as coordinates. And obviously, yeah, so we can do this even stronger. So when we have 2 points, then we have additional parameter called sign. That is simply the 2 and 2 determinant on the vectors of that is determined by P1, P2, and then we have a distance matrix when we have the center of mass and the 2 points, and then sign, and then the distance matrix from the 2 points, and then we have additional matrix that consists of all the other points that were not fixed. So the distance from all the other points that were not fixed to the 2 fixed points and to the center of mass. And so this way, from combining the sign, this G and R for fixed 2 points, we get another invariant. And when we consider, I think, all the combinations of 2 points, then actually we can reconstruct the original graph. So there is invertibility when we have all those 3. And here is a definition of center representation. So basically, yeah, so here's the, I think, a simpler variation from the previous slide. So when we fix a single vertex, then we have first a pair from actually distance from the center of mass to the P1 that is fixed. Then we have this matrix R, so all the distances excluding P1 to the P1 and to the center of mass, and we get this triple. And for 2 points, the example was there, and then the CR is simply that it contains all the combinations. So in case of when A is like consists of only 1 point, then we will have like n entries. But when we have 2 points, then there's a quadratic number of entries. So all the combinations of 2. And we have like this triple for every combination. And the also this mechanic kind of, or we use this mechanic for in the nested way. So so obviously for 1 it's just as it was before, but for the 2 we can actually first fix 1 point, and then after that fix the second point. So it becomes a nested structure. And this will be helpful when we actually compute distances between those two complicated objects. So is there a metric defined here? I think it will be in the following slides, but basically the necessary structure will allow to us to use to reconstruct the point cloud and use the metrics correctly at the same time. So, and before actually going to the metric, I will just quickly introduce the strength is that because we had this triplet here, and we need to compute the distance between the triplets. So if we have just the sign, then obviously the issue is that it can be either -1 or +1. And if some molecules degenerate, its sign can actually go very fast from -1 to +1. So there won't be continuity. So because of that, when we compare sign, we actually need this notion of strength. So it actually measures. So in the degenerate case, when the molecule is, for example, flat or something like that, then, or in that case, when the points that are there will be on the same plane, then this will give 0, and it will allow us to compute the distance between the signs. But it's basically a volume of the object, which is determined by the points. And so the metric between those complicated objects is that actually it probably makes sense to first take easiest part. So when we fix the 2 points or 1 point in the centered representation, then we have the triplets. And for this for the first part, for the sign, we simply compute, we multiply the sign by the strength, and then simply compute them because the difference between those numbers, and then we have some constant that will guarantee the Lipschitz continuity. Then we had the distance matrices that will be simply, I think, computed as the L infinity metric. And the hardest part is that we have those two last matrices where we had a distance from 2 points to all the other points. So between those two matrices, we compute bottleneck distance. That is simply that it's simply a matching distance. So I think, yeah, it's going to come there. But the idea is basically that we want to minimize the maximal distance between two point clouds and match in such a way that the maximal distance will be minimized. And we have like those 3 components, and we compute the distances as stated here. Then I think the bottleneck distance idea is actually here. So when we have either a graph or, well, for example, just a point cloud in this case, for example, 3 points here, 3 points here, we have this kind of complete graph, or in such a way that every point is connected to, so here's like point cloud A, point cloud B, and every point from cloud A is connected to cloud B. And we can, for example, take the Euclidean distance or the any other distance, and then we simply run this algorithm that minimizes the maximal distance. So for example, this will be connected here, this can be connected here, and this here. So we find this matching that minimizes the max distance. And then so we had defined previously the metric between those when we have had the points fixed, but then obviously we also need to kind of compute the distance between those components. So for example, in case we have fixed 1 point, we will have the like n complicated objects on left side, n complicated objects on the right side, one for one molecule, other for the other molecule. And in this case, we simply compute the final bottleneck distance, since we know the distance between all those kind of complicated parts. and when H is 2, or then we use the nested structure. So we had fixed 1, then we fixed 2. We know the distance between the two; those are computed. Then we know the distance at those. Then we are back to the case when we have n of complicated objects. Then we are again compute the bottleneck distance. So there's like a lot of bottleneck distance computations, and in the end, actually in our paper, we had showed that this invariant, together with the metric that I have introduced, is actually a complete. It's also Lipschitz continuous, and it's and computable in polynomial time. So here's just the summary. So we have the from the easiest ones, we have like sorted distance vector here. We have sorted radio vectors and PDDs, and here's the hierarchy that in the end we see that I think that that we can get like from the more complicated to the easier one. We can always go back and get them, but also that usually the more complicated the invariant is, then harder is to compute it. And so here is just the summary of those. So the sorted radio distance vector is fast to compute. Then we have this SDV that is a bit harder, but also contains much more information. Then we have PDD, that a bit more complicated metric, and then we have a variation of our NCD invariant that can be also computed quicker, but might not be complete. And then we obviously have the complete when we have chosen the correct number of points that we are fixing at each stage there. And all those are obviously Lipschitz continuous. And here here's just a summary slide for the databases. We have mostly in this talk and experiments used QM9, but also there's like more bigger database, GEOM drugs, where we have much more of the molecules, and for those we only have used much simpler invariants to to do stuff, because obviously it will take a lot of memory to use something more complicated. And so for the experiment part, in our paper we actually have to demonstrate the effectivity of our algorithm in the two-dimensional case. We actually have projected all the molecules to the two principal directions that are closer to actually have like because there are lots of molecules are flat in the sense that that when we look at them visually, then they're on the same plane. So we have projected the molecules on the plane that that makes sense, and then also molecules that are almost flat, that if we remove the hydrogens, then they're flat. So we have run experiments for those, and so here is the hierarchy. So we start from from the large number, then we compare all of them, then we take 20% closest, go to more complicated invariant, 20% closest and more complicated, and in the end we compute the last ones only for the most complicated invariant is computed only for a handful of the molecules. And here is the number of the number of computations we have made, or comparison between two molecules. And in this slide we have basically we show that the smallest distance when we find different molecules. So the smaller distance than that, we always have the same compositions, and this is the smallest distance when the differences occur. So so when the distance is large enough, then we always have different molecules. We have experimentally verified this, and here's example. So those two are almost the same, but our invariant luckily catches this different bond here, and also our most complicated invariant can actually distinguish between the mirror images. And here's the summary slide. So that in both data sets we have always distinguished those geometrically, and then LCD2 does it very well, and then that the map that we have shown is actually complete and ejective and so on, and yeah, that the chemical compositions can be reconstructed from the geometry. So this is it.
Okay, thank you, Yury. I'll stop the recording.